In this video, we're going to talk a little bit about ionic compounds. And specifically, we're going to think about the empirical formulas for ionic compounds. So the first thing you might be wondering is, well, refresh me, Sal, on what an ionic compound is. Well, we're going to be dealing with ions, which you can view as the charged versions of atoms. So if you start with a neutral atom, the only way it gets charged is if you are gaining or losing electrons, and that would make it an ion. And a compound, that tells us that we're dealing with more than one type of element. So let's just get a little bit of a refresher here. So we talk about this in depth in other videos, but we know that atoms like to have a full outer shell of electrons, a full number of valence electrons. Now, in most situations, that means having 8 valence electrons. And that's why these noble gases right over here are considered to be so stable. They're already very satisfied. They have 8 valence electrons. They all have different numbers of electrons, but that outer shell is 8. And the one exception is when we're talking about that first shell. And once again, this is all review that we talk about in other videos. That first shell is most stable when it has 2 electrons. And that's why helium is also so stable. So in general, when atoms react, they tend to react in a way that gets them to either 2 electrons in their first shell or 8 electrons in any other outer shell, whichever one is their outermost shell. Now, how they get that, they can do that in several different ways, and it really depends on whether we're talking about metals or nonmetals. So first, let me separate the nonmetals here. So hydrogen is a nonmetal, and then we'll come here, and we'll do this little staircase-looking thing. So everything to the right and up of this dividing line that I just drew, these are all nonmetals, including hydrogen. Now, when nonmetals interact to try to get to that full outer shell, they tend to do it by sharing electrons with each other. For example, 2 hydrogens, each of which have 1 outer electron, well, they can form a covalent bond, which we talk about in other videos, and then they're each sharing each other's electrons so they can kind of pretend like they have a full outer shell. Now, it's different when we're talking about a nonmetal interacting with a metal, which we can generally refer to the rest of the periodic table. There's other further subclassifications. When you have a metal interacting with a nonmetal, what typically happens is that the nonmetal is actually going to gain electrons to get to a full outer shell, while the metal will lose electrons to get to a full outer shell. So I'll give you an example, and I use this example a lot, and this is a common example that gets us to table salt. If you look at sodium right over here, a neutral sodium atom has 1 valence electron, 1 electron in that third shell. Well, the easiest way for it to get to a full outer shell is to give up that 1 electron, and then it will have the same number of electrons as neon. It still has 11 protons, which make it a sodium, but it'll have the same number of electrons as neon, and then it will be happy. So sodium tends to form a sodium ion with a positive 1 charge. Now we can go on the other side of the periodic table. If we were to look at chlorine right over here, chlorine has 7 valence electrons. It has 7 electrons in that third shell. Well, the easiest way for it to get a full 8 is to nab an electron from someplace, is to gain an electron. So chlorine tends to take electrons from other atoms and forms a negative charge and becomes the chloride anion. Now, what do you think will happen if you put a bunch of sodium and a bunch of chlorine together? Well, the chlorine's probably going to take electrons from the sodium, or the sodium is likely to give electrons to the chlorine. And then you have these 2 ions. One is positively charged, one is negatively charged. They will be attracted to each other, and that's what forms the ionic compound sodium chloride. And this is the empirical formula for table salt for sodium chloride. For every sodium ion, you have a chloride ion. It's interesting to note that even though the sodium has a positive charge, the chlorine, which is now the chloride anion, has a negative charge, that the ionic compound in total has a neutral charge, which is an interesting property of these ionic compounds.